Swayam Prabha. Digital India. Educated India.
Welcome to Module D, Lecture 7. In this lecture, we shall discuss about analysis of urban street segments as per Highway Capacity Manual 2016. In Lecture 5 and Lecture 6, we discussed about two-lane highway segments. Especially in Lecture 6, we discussed about the framework for LOS determination for class 1, class 2 and class 3 two-lane highways, then mentioned to you about the computational steps, how stepwise we should do the calculation, and then took an example problem to explain you the application. With this background, today we are going to discuss a different types of facility, that is urban streets, and specifically urban street segments. Now, the term urban street is used to refer roadways, particularly in developed areas, that provide access to abutting properties. Access is important because urban area is normally densely developed, and also to provide mobility to vehicular traffic. And pedestrians are there, vehicular traffic is there, bicycle will be there, transit will be there. So, different modes of transport, both motorized and non-motorized, are using such facilities. Normally, access to these facilities is controlled through driveway locations, medians and intersection of other roadways, and in fully developed urban areas, we normally expect large number of signalized intersections. Although there are other types of intersection, stop controlled, yield controlled, those will be there, but also a large number of intersections is actually signalized intersections. Now, the two elements which are commonly found in an urban street system, one we can call points and the others we may call as links. Point is the boundary between links and represented by an intersection, or sometimes it could be a ramp terminal as well. So, we can say that it is the boundary between links. And then what is link? Link is the length of roadway between 2 points. So, generally speaking, if intersections are my points, then the distance between two signalized intersections is my link, and a link and its boundary intersections together, a link and its boundary intersections together, we may call it a segment. Now, if you look at urban street facility, as I have shown here, how the link is defined, how the segment is defined, then urban street facility is actually a length of roadway that is composed of contiguous urban street segments, and is typically functionally classified as an urban arterial or collector streets. You know what collector street functions and what urban arterials are expected to serve. Urban arterial mobility function will be higher than the collector streets. Similarly, the access function will be higher for collector streets as compared to urban arterials. Now, we then have at a larger scale we can consider urban street facility, and then at a detailed level or at a micro level, in that sense we can say that we have segments. Now, the question is, there are two different things, urban street facilities and urban street segments. Particularly, if you try to look at the procedures for analyzing urban street facilities and urban street segments, there are differences. So, what we are going to focus in today's lecture and also maybe the next one or two more lectures is on analysis of urban street segments, not the facility as a whole, not the urban street facilities. We are focusing on specifically urban street segment. Now, urban street segment, like a segment, an isolated segment, similarly it could be an intersection also. Similar kind of analysis may be valid for intersections also, but detailed analysis of signalized intersections, that we will cover in the next module, which is module E. And since we are going to cover the intersections, signalized intersections in particular in quite in a detailed manner, so we shall skip much discussion related to signalized intersection in this module, and our entire focus is specifically on urban street segments, where remember that segment includes a link and its boundary intersection. Now, the link and its boundary points are evaluated together or considered together to provide an accurate indication of the overall segment performance. We cannot take out one element from the other. Here it is important to mention that for a given direction of travel along the segment, link and downstream point performance measures are combined more specifically. So, when we are taking a segment, we are taking a link and the downstream point and its performance to combine and therefore determine the overall segment performance. So, you can consider the link and also the downstream point, the performance of both combined together to say what will be the overall performance of the segment. Now, going to type of control and system of operations. When we are talking about the segment, specifically our focus is on segment, and also probably I missed to highlight this part, that also our focus is for motorized vehicles only, because urban street segments, even also the LOS could be analyzed for motorized vehicle, for pedestrians, for bicycles, for transits. So, we are focusing here only on motorized vehicles, nothing else. So, focus is motorized vehicle performance and on urban street segments. Now, urban street segments are bounded by intersections, which can have a variety of control types, different control types are possible, and different systems of operations are also possible. What we mean by different types of control? That means an intersection could be signalized, could be two-way stop control, could be always stop control, and even it could be roundabout. The methodology may little bit vary depending on what type of control and other factors, but the type of control for such segments and intersections at the used which are actually in use could be different, such as I mentioned, signalized, two-way stop control, always stop control, or even a roundabout. Now, I said that different types of control and different systems of operation. What I mean by different systems of operations? That means it could be coordinated, could be non-coordinated. We are going to obviously discuss these things in a more detailed manner in module E, but since I used this terminology coordinated and non-coordinated, what I mean that the intersections may perform just like an isolated intersection. That means, you take only one urban intersection, consider its input and try to analyze the operation. An operation is happening just considering that intersection as an isolated intersection. That means, we do not bother about other things. We are considering only one intersection at a time. But what happens? That is basically non-coordinated operation, but often you will find traffic moves along a corridor, and typically the direction of movement is very important, because most of the cases you will find heavy vehicle traveling along major arterial towards the city center or CBD. In the evening, the travel is happening mostly in the other direction. So, the major traffic is traveling in a particular direction at a given time, typically morning peak towards the city or CBD area, and therefore, often we find when signals operate in an isolated or non-coordinated manner, then you will leave one intersection, you can see probably the downstream intersection is green, but by the time you reach there, signal turns from green to red. So, when there was no vehicle, because vehicle moves in platoon get discharged, a bunch of vehicle getting discharged from upstream signals and then moving forward, and then majority of the vehicle reach together depending on when and how they are getting discharged and what is the length between signals and many other factors, but they are expected to reach in a bunch, and that time signal is red when probably there is not many vehicle. So, the signal is green at that time. So, what is attempted in a coordinated signal system, the green times of all the signals which are coordinated are adjusted when the green to be given. An attempt is made so that the vehicle once released from an upstream signal, when these vehicles will reach to the downstream signal will give green indication. So, that majority of the vehicles which are arriving at that time can pass through the signals without stopping, and that should happen for all the signals which are actually coordinated. So, you can the whole corridor you can coordinate. You can do coordination in one way, you can do coordination in two way, there are so many other complexities, but that is what we say, that system of operations of signals could be coordinated, could be non-coordinated. Now, here the urban segments, street segments can be analyzed for both systems of operation, coordinated operation as well as non-coordinated operation. Now, when we are analyzing considering coordinated operation, we recognize the influence of an upstream signalized intersection on the performance of the street segments, because signals are coordinated. So, bunch of vehicle getting released and how they are moving, okay, when they are reaching to the downstream signal, and then the signal timings are also adjusted, that time only you try to give green. So, obviously, when we are analyzing coordinated signal system, the methodology or the analysis procedure recognizes the influence of an upstream signalized intersection on the performance of the street segment. While in case of non-coordinated system, such kind of influence will not be there. So, we can consider that arrival to a boundary intersection are random, not like in a platoon, right, with specific pattern. Every cycle during that analysis period, same thing will keep happening. Here we can say that because signals are not coordinated, so arrival can be considered as random. If the subject segment is within a coordinated signal system, then the following rules apply when the segment boundaries are identified. How we identify the segment boundary? So, if we are taking a segment within a coordinated signal system, then these rules may be applied. 1. A signalized intersection is always used to define a segment boundary. So, there has to be a signalized intersection in the segment boundary. And second, only intersections at which the segment through movement, we are taking a segment and we are talking about segment through movement is uncontrolled, for example, maybe two-way stop controlled, can exist along the segment between the boundaries. So, talking about you take a segment, two boundaries are there. So, we are saying only intersections at which the segment through movement is uncontrolled. That kind of intersections can exist along the segment between the boundaries. When the segment is not within the coordinated signal system, then also certain rules may be applied to identify the segment boundaries. First, an intersection having a control that can impose on the segment through movement a legal requirement to stop or yield must always be used to define a segment boundary. So, there the segment boundary, what kind of intersections will be there? Having a type of control that can impose on the segment through movement a legal requirement to stop or yield. It has to be a stop control or yield control. Another, an intersection at which segment through movement at intersections, an intersection at which the segment through movement is uncontrolled. That means, again two-way stop control intersection example may be used to define a segment boundary, but it is typically not done. The first case is more common. Now, going to the type of analysis, what kind of analysis we want to do. So, what we discussed so far, a background and then type of control and system of operation, coordinated, non-coordinated and so on. The type of analysis, the phrase analysis type is used to describe the purpose for which the methodology is, for what purpose we are doing this analysis. So, the purpose will determine what kind of analysis is required, and each purpose is associated with a different level of detail. The purpose will determine or influence or control what level of detail is required. Since it relates the precision of the input data, also will dictate how much precision data is required, how many default values can be assumed for analysis, or I have to go on to the field and everything context specific data I have to get, and how much accuracy I require for the analysis. It depends on the level of detail, right. It is all include level of detail or the purpose. Some purposes may be a more detailed analysis is required, a much more accuracy, higher accuracy is expected, but for certain other kinds of purposes, the required accuracy may not be that high. So, there are three analysis types are recognized: operational, the most detailed one obviously, practically everything you want to collect from the field because it is operational level analysis, then design level analysis and planning and preliminary engineering level analysis. Now, when it is planning and preliminary engineering, many things are not even known. We may have certain forecasts, certain specifications, certain ideas. So, many things we can assume. Simpler analysis we can do, because my purpose is to do a planning and preliminary engineering level analysis. But if I want to do operational level analysis, then I have to go for a more rigorous database. I cannot assume much, and the methodology also has to be different for different types of analysis. Operational analysis focuses on current or near term conditions and requires detailed inputs, as I said, with practically no or minimal use of default values. It will not work that I will assume many things. We cannot assume, because it is operational level analysis. You go to the field and get the data. So, data collection effort and more rigorous data, more rigorous analysis also needs to be done. Design analysis is typically carried out for a facility using some default values, not like operational analysis where we practically do not use any default values or make it minimum, but here some default values we use, and it is aimed to identify the characteristics of the facility which are expected to operate at a desired level of service. Characteristics of facilities which are expected to operate at a desired LOS. That is the design level analysis. Planning and preliminary engineering level analysis is carried out with extensive use of default values. Here we use extensive default values, because it is at the planning stage. So, many things are not available, you may not be able to go to the field and measure it, and some of the things you might have decided also, right. Some decisions have been made. So, largely or extensively we are using default values, and the basic aim is to do a quick evaluation of many facilities or alternatives. That is what is done. Planning level always we do that. We want to evaluate alternatives, not we are going for a detailing. So, the purpose is quick evaluation of many facilities or alternatives, or when specific input values are not known. So, it is a quick kind of analysis, simple analysis, and without using extensive field data, because field data may not be available also. So, lot of default values we use. Now, going to the LOS criteria. As I said, our focus is on the street segments, and also as I said that our focus is basically the street segments and also the motorized vehicle. So, the LOS also is based on that, right. Now, two performance measures are used to characterize vehicular LOS for a given direction of travel along an urban street segment. if we know how to calculate the or decide the LOS, two predominant performance measures, others are also there, we will discuss later. A few other things also may be considered as possible measures and are considered also. But when we are saying what is then the LOS, we are using two specific performance measures. One is travel speed for through vehicle, because it is the segment and the through vehicle is the primary objective or our focus. So, through vehicle travel speed, why we are interested? Because it reflects the factors that influence the running time along the link and the delay incurred by through vehicles at the boundary intersections. Second, volume to capacity ratio for through movement at the downstream boundary intersection to reflect the degree of mobility for the segment. How much that it is loaded? Is it loaded more than the capacity or it is within the capacity? Because the effects are going to be very different. So, considering travel speed and volume to capacity ratio, 6 levels of service are defined as follows. LOS A, primarily free flow operations, vehicles are completely unimpeded in their ability to maneuver within the traffic stream. Control delay, it is one type of delay. We will discuss what is exactly control delay in some other lecture when we talk about the intersections and signalized intersections, particularly in module E. And the travel speed exceed 80% of the base free flow speed. You already know what is BFFS, base free flow speeds. We discussed earlier about various other segments. So, here also there is a value for BFFS. So, the travel speed is more than 80% of the BFFS, and obviously all cases from LOS A to E, V by C ratio is less than 1, less than equal to 1. So, A, B, C, D all cases it has to be less than 1 and E may be near capacity. LOS B, reasonably impeded operation, reasonably unimpeded operations, and where the ability to maneuver traffic stream is only slightly restricted. Here it was like free flow, slight deterioration has happened, but still reasonably unimpeded operation, and control delay again is not so significant, lower side. Travel speed is between 67% to 80%. Here it was more than 80%, here it is in the range of 67 to 80% and V by C ratio as usual less than 1. C, stable operation where the ability to maneuver and change lane at mid segment location may be more restricted than what was there under LOS B, and here the travel speed is somewhat between 50 to 67% of BFFS and V by C ratio still less than 1. LOS D, a relatively a less stable condition in which the small increase in flow may cause substantial increase in delay and have a larger impact on the travel speed will come down, and due to adverse signal progression, high volume or inappropriate signal timing, travel speed is somewhat between 40 to 50% further going down, but still the volume to capacity ratio is not more than 1, it is lesser than that. E, characterized by unstable operation almost near capacity, and therefore, significant delay will be there, and due to some combination of adverse progression, high volume and inappropriate signal timing in the boundary intersection, travel speed is only in the range of 30 to 40% of the BFFS. It has come down drastically. and F forced flow. Here first thing, the V by C ratio is greater than 1. So, it is characterized by flow at extremely low speed and congestion likely occurs at the boundary intersection, which is indicated by high delay and extensive queuing. So, overall speed is below 30% of the BFFS. That is the way the whole LOS, different levels of service, are defined and described. So, these are the threshold value as given in Exhibit 18.3 Highway Capacity Manual 2016. You can say A, B, C, D, E, F, except for F all within 1 V by C ratio. V by C ratio greater than 1 means straightway LOSF. So, within 1 5 levels of service, threshold speed are given, different BFFS value, base free flow speed 55, 50, 45, 40, 35, 30 up to 25 mile per hour. Then what is the threshold value for different levels of service? Say for example, if the base free flow speed is 50 mile per hour, then anything greater than 40 mile per hour average speed is actually LOS A, greater than 34, less than 40, somewhat B, and so on. Now, going to operational analysis of level of service. As I said earlier, the analysis could be operational level analysis or it could be planning level analysis. First, the operational level analysis. For motorized vehicle methodology, our focus is motorized vehicle and segments. A segment evaluation consider both directions of travel when the street serves two-way traffic. Earlier, this is a change in this Highway Capacity Manual 2016 as compared to the previous version. So, when we are two-way streets, two-way traffic, then for motorized vehicle methodology, we consider both directions of travel, because there are interdependency. Also, it is assumed that traffic conditions are steady during the analysis period, no systematic change happens during that analysis period, stochastic variations that anyhow will be there. So, it is assumed that the traffic conditions are steady and typically analysis period is taken as 15 minutes to 1 hour. Most cases we take even 15 minutes, but range is actually 15 minutes to 1 hour. And as I said, the operational analysis framework, what we are going to discuss, in that the calculation process, whatever we are going to say, is applicable for both systems, both coordinated and non-coordinated systems. Analysis of coordinated system recognizes the influence of upstream signalized intersection on the performance of street segments. I mentioned this earlier also. And when we are analyzing non-coordinated system, the basic assumption is that arrival to a boundary intersections are random, because the signals are not coordinated. So, always by default for non-coordinated operations, that is the basic assumption. So, here also we make that same assumption. Framework is further subdivided into type of control, could be signalized, two-way stop control, always stop control, like that, used at intersections that bound the segment. Now, here I am going to discuss briefly what you can see. This is the non-coordinated system. Again, it could be pre-timed or actuated. Pre-timed is taking the average, suppose you are doing it for the peak hour. So, you know what is the average peak hour flow from different approaches in a signal, and for the typical peak hour flow you actually design it and operate every day with the or during that entire time with the same signal setting. But actually there will be stochasticity, volume may change for so many reasons also. So, every green time what you are giving, every cycle may not require that much green time. Sometimes every cycle may not, even the green time what you are getting may not be adequate for every cycle also. Some cases the demand may go up, some cycle the demand may go down. So, if you can make it actuated, that means as from sensor you are getting the inputs, accordingly the whole system is getting optimized based on real time data. Now, actuated could be in so many ways, actuation may occur, partly actuated, fully actuated operations. We shall again discuss things in details in module E, but here I just wanted to mention pre-time means fixed inputs we are assuming during that entire period. Say peak hour means the entire peak hour every day is same. So, same signal setting we are operating. Actuated means it could be as we are getting the inputs on a real time basis from sensors, accordingly the whole control is happening. The cycle length or and maybe the green time, phasing, everything will change. Detailing will be changed accordingly. So, for both cases we can do step 1 is determine traffic demand analysis, traffic demand adjustment, lot of adjustment we need to do in the traffic demand considering capacity, considering other factors. Then determine the running time. Step 3 determine proportion arriving during green, that is very important for signal control. And then step 4 includes determine signal phase duration, here also the same. Then we check whether the convergence has happened. If no, then we are again going back, doing again necessary adjustment in the traffic demand and keep on repeating this procedure unless the whole thing is stabilized. And once convergence has happened, then we calculate the through delay. And if it is also, since it is non-coordinated system, the intersection could be stop controlled, yield controlled or even uncontrolled. So, in that case this signal part determine the proportion arriving during green, phase determination, all this need not be done. So, directly we can come from this step 2 to step 5 to determine the through delay, and then once the delay is known, then we want to determine the through stop rates, then the travel speed is determined, also the spatial stop rate, and then accordingly determine the level of service. Then also as I said that LOS definitely is important, but traveler's perception may depend on not only the travel speed, but many other factors, right. The spatial stop rate, right, all this, that is why we have calculated. So, we can also calculate the automobile traveler overall perception score, how good or bad they feel. We can express it not only in terms of level of service, but also based on the perception score. Now, the methodology for coordinated signal system is, the steps are more or less same, except the fact that since it is coordinated system, there cannot be stop, yield or uncontrolled intersections. So, what we consider here is that link is omitted, otherwise the steps are same. Now, the methodology as you can see is iterative up to step 1, from step 1 to step 4, and then we are checking this convergence. If no, then we are going back. If no, we are going back. If no, we are going back. Only we are coming out when the answer is yes, the convergence has happened. So, step 1 to step 4 therefore, is clearly iterative in nature. With convergence achieved, we are saying convergence yes or no. What we mean by convergence? Convergence means when the predicted discharge volume, phase duration and capacity, discharge volume, how much is the discharge volume, what is the phase duration and what is the capacity, that we are calculating at different steps, when from successive iterations the calculations do not change, then we say that it is effectively in agreement. So, then it is yes, otherwise do further adjustment. Normally, several iterations are typically needed for coordinated system to stabilize the process, stabilize these values, as I say predicted discharge volume, phase duration and capacity, but generally only one iteration is needed for non-coordinated system unless there is a downstream closure. Downstream closure, that means what happens, ln may be closed downstream. So, in that case we may require multiple iterations to ensure that the vehicle discharge upstream of the lane closure do not, because there the capacity may be more, but there is a bottleneck. So, the vehicle discharge upstream of the lane closure we have to check, so that do not exceed the lane closure capacity. Ultimately, what can get discharged is only the lane closure capacity. So, the upstream vehicle discharge upstream of lane closure do not exceed the lane closure capacity, that has to be maintained. So, we may require multiple iterations. So, altogether what we discussed in today's lecture is I gave you introduction to urban street segment, discussed about various types of control and various systems of operations. Systems mean coordinated, uncoordinated, both. Then we talked about types of analysis, planning level analysis, design level analysis and operational level analysis, mentioned about the LOS criteria and how the LOS is defined or described, and then just indicated to you the operational analysis framework. Now, in the next lecture I am going to discuss little bit more about each of these 10 steps. I only mentioned to you the flow chart today and just mentioned to you about the steps. Further description discussion we shall make in the next class. Thank you so much.